If I told you to picture the world's first nuclear reactor, you'd you'd probably imagine this sterile, highly classified laboratory somewhere in the 1940s, right?
Yeah, I mean, you definitely picture scientists in lab coats.
Exactly, like Oppenheimer or Fermi just standing around looking very serious. But according to the stack of research on the table today, you would be wrong by like about 2 billion years.
Right. Which is just, it's wild to even think about.
It is. The very first nuclear reactor wasn't built by a government or, some team of brilliant physicists. It was built entirely by accident, by Mother Nature, in a rock formation in West Africa.
Yeah, it's honestly one of the most incredible geological discoveries of the 20th century. And it completely rewrites how we think about atomic energy. I mean, it takes this concept that feels impossibly modern and grounds it in the deep, ancient history of the Earth.
It really does. So welcome to another deep dive. Today, our mission is to cut through the heavy scientific jargon, and there's a lot of it in these sources.
Oh yeah, tons of dense physics equations.
So much information overload. We're looking at a very comprehensive encyclopedia overview on nuclear reactors today. It covers literally everything, from the foundational quantum physics of the 1940s all the way to futuristic Generation V plus technologies.
Right, the stuff that sounds like pure science fiction.
Exactly. But we want to answer a surprisingly simple question for you today. What is actually happening inside those massive concrete domes you see off the highway? And how on earth did humanity figure it out?
It's a massive topic. I mean, we are essentially talking about how human beings learn to harness the fundamental binding forces of the universe just to, keep the lights on.
Okay, let's unpack this. Because starting with that mind bender in Gabon, West Africa, completely flipped my perspective on this whole thing.
The Oklo site.
Right. The sources detail this region called Oklo, where around 1.5 to 2 billion years ago, 15 natural fission reactors just like self-assembled in the ground and started running.
Yeah.
I mean, how does a rock formation spontaneously start splitting atoms?
Well, it required a literal perfect storm of geological and physical conditions. You had a mineral deposit there that was just incredibly rich in uranium.
Okay.
Now, at that specific time in Earth's history, the natural concentration of the highly fissile isotope, uranium-235, was much, much higher than it is today.
Right, because it naturally decays over time.
Exactly. So 2 billion years ago, there was plenty of it. But having the uranium wasn't enough. The reactor didn't actually start until groundwater flooded the porous deposit.
See, I read that part in the notes, and I honestly had a hard time wrapping my head around it. The water acts as what was the term? A neutron moderator.
Yes, a neutron moderator.
But why does flooding a bunch of radioactive rocks with water cause them to react more? Shouldn't it, I don't know, put the fire out?
It is deeply counterintuitive, yeah. To understand it, you have to look at the mechanics of splitting an atom. When a uranium-235 atom naturally decays and spits out a neutron, that neutron is moving incredibly fast.
Think fraction of the speed of light fast.
Exactly. Super fast. And if it hits another uranium nucleus at that extreme speed, it actually just bounces right off. It's moving way too fast to be captured by the nucleus.
Oh, okay. So it's kind of like trying to put a golf ball. If you hit the ball way too hard, it just skips right over the hole and lips out.
Right.
You have to slow the ball down so gravity can actually pull it down into the cup.
That is a brilliant way to visualize it. Except, instead of gravity, we're talking about the strong nuclear force.
Sure.
But the principle is the same. The fast neutrons need to be slowed down or moderated, so they spend enough time in the immediate vicinity of the uranium nucleus to actually be snatched up by it.
Got it.
So when the groundwater flooded the Oklo deposit, the fast neutrons crashed into the water molecules, lost their kinetic energy, and slowed down to that perfect putting speed, as you called it.
And that triggered the chain reaction.
Exactly. That triggered a self-sustaining nuclear chain reaction.
So nature basically built an atom-powered geyser.
Basically, yeah.
But wait, why didn't it just instantly explode into a massive crater? I mean, it's a nuclear reaction.
Well, that's because of the water's dual role. So the reaction generated about 100 kilowatts of thermal power, and as the uranium heated up the surrounding rock, it boiled the groundwater away, turning it into steam.
Okay, that makes sense.
But remember, the liquid water was the moderator. Once the water boiled away, there was nothing to slow the neutrons down. They were moving too fast again.
The golf balls started skipping over the holes.
Exactly. And so the chain reaction simply stopped.
Wow. That is an incredibly elegant feedback loop.
Right.
It heats up, boils off the water, shuts itself down, cools off, the water seeps back in, and it starts all over again. The sources say this natural cycle pulsed like a heartbeat for hundreds of thousands of years.
It really is amazing. And what's fascinating here is how scientists actually use the Oklo site today.
Oh, really? How so?
Well, these ancient natural reactors are studied as a perfect case study for modern geological waste disposal.
Oh, that makes sense.
Yeah, by analyzing the surrounding rock, scientists can see exactly how radioactive isotopes migrate, or, crucially, how they don't migrate through the Earth's crust over billions of years. It directly informs how we design long-term storage for human-made nuclear waste today.
Okay, I have to pause you there, though. Because if nature can just accidentally build a self-regulating nuclear reactor with some rocks and groundwater, why aren't mountains spontaneously going critical today? I mean, why don't we see this happening all over the globe?
It all comes down to half-lives. Like we touched on earlier, over the last 2 billion years, that highly fissile uranium-235 isotope has been steadily decaying.
Right.
Today, its natural concentration in uranium ore is less than 1%. That is just far too low to sustain a chain reaction with just plain water as a moderator.
So the Earth is just too old now.
Yeah, the Earth has simply aged out of its ability to do this on its own.
So because nature can no longer trigger these reactions, human beings had to step in and engineer the conditions ourselves. Which brings us to the inside of those massive concrete domes. What exactly are we engineering in there?
We're engineering a highly controlled environment for fission. Let's look at the mechanics. When that moderated, slow-moving neutron gets captured by a uranium-235 nucleus, the nucleus becomes hopelessly unstable.
It can't hold itself together.
Right. It violently splits apart into two lighter elements, and when it splits, it releases kinetic energy, gamma radiation, and 2 or 3 more free neutrons.
And those 2 or 3 new neutrons get slowed down by the water, they hit other uranium atoms, which split, release more neutrons, and suddenly you have your exponential chain reaction.
Precisely. And the energy density of this physical process is almost incomprehensible.
The sources had a crazy stat on that.
Yeah, they point out that if you take just 1 kilogram of uranium-235 and put it through this fission process, it releases about 3 million times more energy than conventionally burning a kilogram of coal.
3 million times.
It's staggering.
But here is the massive irony hidden in all this cutting-edge quantum physics. We split the fundamental building blocks of the universe. We release this godlike cosmic energy, and what do we actually do with it?
Oh, I know where you're going with this.
We use it to boil water.
It is the great paradox of nuclear power.
I mean, a commercial nuclear reactor is essentially just the most complex, heavily shielded, expensive way ever invented to boil water, create highly pressurized steam, and use that steam to spin a giant fan the turbine to generate electricity.
Yeah.
It's exactly how a coal plant works, just with a much spicier heat source.
Spicier. That's one word for it. But yeah, it is a very humble mechanical end to a profound quantum beginning. But controlling that quantum beginning is where the real engineering miracle happens.
Because it wants to run away.
Right, exactly.
Yeah.
Because if you just let a chain reaction go, it doubles its power in fractions of a second. The source text highlights a highly critical nuance that actually makes reactor control possible, and it's called delayed neutrons.
Right. I really want to dig into this because the math here totally blew my mind. When the atoms split, the neutrons don't all come out at the exact same time, do they?
No, they don't. The vast majority of neutrons, like over 99% of them, are what we call prompt neutrons. They are released the exact microsecond the uranium atom splits.
Okay.
But about 0.65% of the neutrons are delayed.
0.65. Less than 1%. I mean, in almost any other industry, that is a rounding error. You wouldn't even factor it in.
Oh, absolutely. But in nuclear physics, that fraction of a percent is the entire ballgame.
Really?
Yeah. Those delayed neutrons aren't coming from the initial split. They're trickling out milliseconds to several minutes later, emitted by the radioactive decay of the broken fission fragments left behind.
So they're just trailing behind.
Right. And without those delayed neutrons, the time between the reactor reaching criticality and a catastrophic exponential power surge would be measured in microseconds.
Meaning, if a reactor started running too hot, it would melt down before a human operator could even blink, let alone push a button to stop it.
Exactly. Even an automated computer system couldn't drop the safety mechanisms fast enough.
Wow.
Those delayed neutrons act as a temporal buffer. They slow down the generation time of the chain reaction just enough to give us a split-second window. They are the absolute only reason human beings can control a nuclear chain reaction in real time.
So we're basically balancing a pencil on its tip, and those delayed neutrons are the tiny, invisible fingers keeping it from falling over instantly.
That's a great analogy.
But if the delayed neutrons give us the reaction time, what are the actual brakes we use to steer this thing?
That's where reactivity control comes in. We use physical control rods made of materials that the sources call neutron poisons.
I love that term, neutron poison. It sounds like something straight out of a comic book.
It does, but it's a very descriptive engineering term. Materials like boron or cadmium have a massive atomic cross-section, meaning they're incredibly good at absorbing free neutrons without splitting themselves.
They just soak them up.
Right. So if the reaction in the core is running too hot, operators insert the boron rods deeper into the water. The rods drink up the free neutrons, starving the chain reaction of its fuel, and the power output drops. Pull the rods out, the reaction ramps back up.
But the sources make it very clear that driving a nuclear reactor isn't as simple as just pulling a lever up and down.
Not at all.
There's this bizarre chemical quirk that happens inside the core called xenon poisoning, or the iodine pit. And this really tested my understanding of the chemistry when I was reading it.
It's complex, yeah. But it's a phenomenal example of how dynamic and honestly alive the inside of a reactor core really is.
Walk me through it.
Okay, so when fission happens, one of the leftover broken pieces, the byproducts, is an isotope called iodine-135. Now, iodine-135 is unstable. Over the course of about 6 to 9 hours, it naturally decays into xenon-135.
Okay, tracking so far.
And xenon-135 happens to be one of the most powerful neutron poisons in the known universe. Its atomic cross-section is massive. It acts like a giant catcher's mitt for neutrons.
Wait, so the reactor is literally creating its own poison as a byproduct of running?
Exactly.
Okay, let me try an analogy here to see if I have the physics right. Imagine the reactor is a giant campfire.
Okay.
The uranium is the wood, and the xenon-135 is the ash. As long as the fire is roaring at full power, the intense heat and the updraft constantly blow the ash away.
Right. Like in the reactor, the high flux of neutrons essentially destroys the xenon as fast as it's created.
Yes, that is a highly accurate way to look at it. The reactor burns off the xenon poison while running at a steady high power level.
But if you damp the campfire down, like if you drastically lower the reactor's power or shut it off completely, the updraft stops, the ash settles. And because the iodine is still decaying into xenon, more and more ash keeps falling, completely smothering the glowing embers. You nailed it. When you drop the power, the xenon isn't being destroyed anymore, but it keeps being produced by the decaying iodine, so it builds up to a massive peak.
And it smothers the reaction.
Exactly. If you try to restart the reactor shortly after shutting it down, you literally cannot. The xenon is absorbing all the neutrons before they can hit the uranium. You have fallen into the iodine pit. You just have to wait a day or two for the xenon ash to naturally decay away before you can turn the reactor back on.
That is wild.
And if we connect this to the bigger picture, understanding this specific xenon transient is absolutely crucial for safety.
Right.
The source material impartially notes that a failure by operators to respect this exact xenon buildup was a massive contributing factor in the 1986 Chernobyl disaster.
Oh, really?
Yeah, they had powered down, fell into the xenon pit, and then tried to force the reactor to power back up while it was heavily poisoned. They pulled almost all the control rods out to fight the xenon, which created an incredibly unstable, precarious core state just before the fatal power surge.
Man. It really highlights how much profound respect this physics demands. You aren't just managing heat, you're managing the invisible, shifting atomic makeup of the fuel moment by moment.
It's incredibly delicate.
And understanding this staggering complexity makes the historical reality of the first human-made reactor seem almost absurd.
Oh, it's a stark contrast. I mean, the theoretical concept of the nuclear chain reaction was only just realized by Leo Szilard in 1933.
That's not that long ago.
No, it's not. But it wasn't until December of 1942 that a team led by Enrico Fermi actually achieved it in the real world.
Here's where it gets really interesting. I want you to imagine the scene. You are standing in the freezing cold beneath the viewing stands of the abandoned squash courts at the University of Chicago. You're looking at Chicago Pile 1. And they called it an atomic pile because they literally just piled things up.
They really did. It was a rudimentary structure made of rough wood supporting a literal pile of black graphite blocks.
Just graphite blocks stacked on top of each other.
Yep.
The graphite acted as the neutron moderator, doing the job the water did at Oklo. And interspersed within those dusty graphite blocks were roughly pressed natural uranium oxide briquettes.
Wood. They built the world's first nuclear reactor out of wood, graphite dust, and uranium briquettes.
Pretty much.
There were no massive concrete containment domes, no highly pressurized water cooling loops, Just a team of scientists with slide rules, standing around a wooden scaffold, knowing that if their math was wrong, a significant portion of Chicago might disappear.
It was incredibly brave.
But they proved that humanity could command the atom.
They did. Now, it was purely a proof of concept. I mean, it generated just a fraction of a single watt of power initially, but it proved the underlying physics were sound.
And then things move fast.
Very fast. From that cold squash court, the technology accelerated at a breakneck pace. By 1954, just 12 years later, the Soviet Union's Obninsk plant became the first civil nuclear power plant to produce electricity for a grid.
Wow, just 12 years.
Yeah, quickly followed by Calder Hall in England in 1956. So we go from a wooden pile in Chicago, generating half a watt, to gigawatt power grids. How has this technology evolved since then? Because looking at the sources today, we have quite the reactor menagerie operating around the globe.
We do. According to the data, as of 2025, there are over 400 commercial reactors operating worldwide. They quietly keep the lights on for about 9% of the total global electricity supply.
9%, that's huge.
It is, and the vast majority of those, almost 90%, are either pressurized water reactors or boiling water reactors.
Okay, so these are the giant hyper-complex water kettles we talked about earlier.
Exactly.
But the text highlights a growing systemic issue across this entire global fleet. They're getting old.
Yes, aging is a major factor right now.
Modern plants being designed today are built for a 60-year lifespan. But a lot of the older plants currently running were originally planned for 30 or 40 years of operation. Now, regulators are extending their licenses to run for 60 or even up to 80 years.
Which is a very long time for an industrial facility.
That's what I'm saying. Let me pose a question to you. I can barely keep my laptop running for 5 years.
Huh.
Is it mechanically sound to run a nuclear facility every single day for 8 decades?
It is one of the most significant engineering challenges in the energy sector today, for sure. But you have to look at how a plant is maintained. Most of the active components of a nuclear power plant are constantly swapped out.
Okay.
The massive cooling pumps, the miles of electrical wiring, the steam turbines, even the gigantic steam generators themselves, all of that can be replaced as it ages.
Right, so you're essentially swapping out every moving part over the decades to keep the facility modernized. It's kind of a ship of Theseus situation.
Exactly. However, there's a hard physical limit, and that limit is defined by the core components that absolutely cannot be replaced. The primary bottleneck is the reactor pressure vessel itself.
The vessel. That's the giant, incredibly thick steel container that actually holds the radioactive core and the highly pressurized water, right?
That's the one.
But why can't that last forever? I mean, it's just thick steel, isn't it?
It is, but because of a microscopic process called Neutron Embrittlement, remember those incredibly fast neutrons flying out of the splitting uranium atoms?
The ones that need to be moderated.
Right. Well, a lot of them escape the fuel rods and smash directly into the steel walls of the pressure vessel. And steel is not just a solid block. It's made of a neat, orderly, crystalline lattice of iron atoms.
Okay, so the free neutrons are acting like microscopic bowling balls, slamming into a pristine rack of pins.
That is exactly what happens. Over decades of constant operation, trillions of these neutron bowling balls violently knock iron atoms out of their crystalline alignment.
Ouch.
On a microscopic level, this creates tiny voids and defects. It's essentially microscopic scar tissue inside the metal. Over time, the steel slowly loses its ductility, its ability to flex under pressure, and becomes brittle.
And you can't unscar the steel.
No, you can't.
And you certainly can't easily swap out the most radioactive, deeply embedded structural component of the entire plant.
Precisely. So, while regulators may push paper to extend an operating license to 80 years, physics has the final say. If metallurgical inspections show too much embrittlement, or if the economics of trying to retrofit new safety systems around a brittle vessel don't make financial sense, the plant will be shut down and decommissioned long before that license expires.
Which naturally brings us to a topic we absolutely have to discuss. You cannot talk about operating an aging fleet of nuclear power plants without addressing the safety, the waste, and the environmental impact.
No, you really can't.
The source material spends a good amount of time impartially breaking down the data on both sides of this equation, and it is a fascinating dichotomy.
It is vital to look at the full, unvarnished picture. On one side of the ledger, you have the severe reality of accidents and waste. The text specifically details level 7 disasters, which are the highest on the international severity scale. Chernobyl, which was driven by design flaws and operator error, and the 2011 Fukushima disaster. In the case of Fukushima, the sources note the specific mechanism of failure. It wasn't the earthquake that caused the meltdown, but the subsequent massive tsunami that critically flooded and disabled the backup diesel cooling systems.
Right, which led to a loss of the heat sink.
Exactly.
And beyond those rare accidents, there is the daily reality of the waste. The spent nuclear fuel that operators pull out of the reactor is highly toxic, and it remains a radiological hazard for thousands of years.
It's a massive responsibility.
The procedure outlined in the text is intense. This spent fuel must first be submerged on-site in deep, heavily circulated spent fuel pools for roughly 5 years, just to let the immediate thermal heat and intense radiation cool down.
Right, because those broken fission fragments we discussed earlier, the ones creating the delayed neutrons, they are still furiously decaying.
Right.
And after those 5 years, the fuel is transferred into massive, dry, heavily shielded storage casks and placed in impervious concrete bunkers.
So that is the heavy burden of nuclear power. Managing millennial-scale toxic waste, guarding it, and engineering against the severe consequences of rare, catastrophic accidents.
Yes.
But on the other side of the ledger, you have the environmental footprint of daily operations. And this is where the data from the source has genuinely stopped me in my tracks. Because the daily atmospheric emissions from a functioning nuclear plant are staggeringly low.
They are almost negligible compared to fossil fuels. The sources gave a highly specific comparison regarding trace radiation releases.
Right, so nuclear plants occasionally release tiny amounts of tritium, which is a radioactive isotope of hydrogen, into the environment. The U.S. Nuclear Regulatory Commission estimates that if a person were to drink exclusively from a water well contaminated by a significant tritiated water spill from a nuclear plant for an entire year,
An entire year.
they would receive a radiation dose of 0.3 millirem.
And to put that 0.3 millirem into human context, the text points out that taking a single round-trip commercial airplane flight from Washington, D.C. to Los Angeles exposes you to 4 millirem of radiation.
Or millirem.
Yeah.
Just from flying.
Simply because flying at 35,000 feet means you have less of the Earth's atmosphere protecting you from natural cosmic rays bombarding the planet from space.
So a full year of drinking contaminated well water right next to a nuclear plant gives you less than 1/10 of the radiation exposure of taking one cross-country business flight.
It's wild, and this raises an important question, and it perfectly encapsulates the unique paradox of nuclear energy presented in the text.
Yep.
As a society, we have harnessed a technology that requires flawlessly managing highly toxic waste for millennia to prevent regional contamination. Yet simultaneously, its daily atmospheric radiation footprint and its contribution to global carbon emissions during normal, everyday operation is an order of magnitude less than getting on a commercial airliner.
It's a lot to wrap your head around. So what does this all mean for you listening? We have gone from groundwater boiling inside ancient African uranium deposits 1.5 billion years ago to Enrico Fermi stacking firewood and graphite under a squash court to these hyper-complex, aging, water-boiling behemoths that currently power nearly 1/10 of the globe.
It is an incredible, mathematically gorgeous, yet incredibly fraught legacy. It's a technology entirely defined by its extremes.
Extremes in every direction.
Extreme energy density, extreme safety engineering requirements, and the extreme longevity of its byproducts.
Well, to leave you with something to really mull over, I want to look past the current reactors and bring up a concept mentioned right at the very end of our source material.
Whoa, this is the good stuff.
We established earlier that today's commercial nuclear reactors are basically just glorified water boilers, right? We are using the most advanced quantum physics on Earth just to make steam to spin a metal turbine.
It is a profoundly indirect, thermally inefficient way of capturing the energy of the atom.
Right. But the sources outline a theoretical Generation V+ concept called the Fission Fragment Reactor.
Yeah.
And this design completely bypasses the water, the steam, and the turbine.
Yeah.
I mean, how do we stop boiling water?
You have to look at the exact moment of fission. When the uranium atom splits, the two halves, the fission fragments, fly apart at roughly 3% the speed of light.
3%.
That is pure, raw kinetic energy. In a normal reactor, those fragments immediately smash into the surrounding water molecules, generating friction and heat.
But in a fission fragment reactor, we don't let them hit water, we do it in a vacuum.
Exactly. And because these fission fragments just went through a violent split, they are missing a lot of electrons. There are highly positively charged ions,
Yeah.
and because they carry a massive electrical charge, we can manipulate them using powerful magnetic fields.
So instead of making heat, you use giant electromagnets to catch these microscopic fragments flying at 3% the speed of light. And as those charged particles push against the magnetic field to decelerate, that magnetic resistance directly induces an electrical current in a surrounding wire coil.
Precisely. You are converting the kinetic energy of the splitting atom directly into an electrical current. No water, no steam, no moving mechanical parts whatsoever.
That's incredible.
And by entirely skipping the thermal conversion process, the theoretical efficiency of the power plant jumps from about 40% in a modern steam plant all the way up to 90%.
It is entirely mind-bending. I want you to imagine a future where we stop treating the atom like it's just a very hot piece of coal. A future where we finally stop boiling water, and we figure out how to plug our electrical grid directly into the splitting atom itself.
It's quite the vision.
We started this deep dive talking about the leap from chemical fire to nuclear fission. Maybe the next great leap isn't finding a new fuel to burn, but finally leaving the fire metaphor behind for good.
A truly fascinating thought to end on. It shows that our journey with the atom is really only just beginning.
It really is. Thanks for taking this deep dive with us. We'll see you next time.